All right, we're talking about phenomenon associated with our atmosphere. One that we haven't mentioned yet is called the temperature inversion. I mentioned that in the early morning hours, as the surface of the earth begins to heat up, as the day begins to form, the warm air expands, therefore it's less dense. It wants to rise. The cold air above it is more dense. It wants to sink. And eventually it will change places. It will recirculate. The warm air will rise in thunderheads, and then in the afternoon, everything will reach equilibrium. It will balance out. However, there is a condition to where you can form a cap of cold air, like a Tupperware seal, that doesn't allow the warm air to escape throughout the day. And when that occurs, they call that a temperature inversion. It's bad because since the earth is not the water's not, the air is not circulating, it causes all the pollutants to build up. And you can generally see it. This is a graph that was taken of a temperature inversion at cold air. You can see all the pollution that's collecting underneath it. Generally, when you have temperature inversions like this around urban areas where there's lots and lots of pollution from factories and cars, it will actually have warnings where people can't go out on the streets. The air is unhealthy to breathe, especially if you have some kind of respiratory problem or asthma or something like that. Generally, these types of temperature inversions occur in cities that are built in depressions, in bowl-shaped depressions. For instance, Denver, Colorado, Nashville, Tennessee, San Bernardino, California, are notorious for being built down inside of one of these bowl-shaped depressions, which allows the caps to form fairly easily. Dallas, from time to time, will have temperature inversions. You may have seen them when you're driving to Dallas and you see that layer of kind of dark air down low. Most likely that's a temperature inversion. Whenever you see white smoke, that's not pollution. I know it looks really bad, but it's not. White smoke is actually water vapor, which is good. It's just water. It's like a cloud. Real pollution is when you see gray or black type smoke. Another feature of the atmosphere is called a mirage. You've probably seen it. They're very common. You're driving and you look out and it looks like a lake. It's not a lake. What is happening to generate a mirage? A mirage is formed whenever you have a very well-defined boundary between warm air and cool air. Even though you can't see the boundary with your eyes, the light will interact with that boundary. It will bounce off of it, just like the light bounces off the surface of a mirror or a piece of glass or a burnished pot where you can see your reflection. And so what's happening here in this photograph is probably about right here. There is a very well-defined boundary between the warm air below and the cold air above. And as the light is coming from these donkeys in the distance, there's light that's coming straight toward our eyes. That's the reason we can see the donkeys. But there's also a part of that light that's going up and hitting that boundary and bouncing back down toward our eyes. Since it hit the boundary and it's bouncing back down, it inverts, it flips it over. And so by the time it makes it to our eyes, it looks like those donkeys are actually here. And so it actually inverts, flips over that image. And so you have the image of the donkeys from the light coming toward us, and you have this other layer that's creating this inverted image, which looks like it's coming off water, but it's not water. And when you get there, you realize that's not water. It's not reflecting off the water. It's not hitting the water and bouncing up toward our eyes. It's hitting this layer above and coming back down toward our eye. Here's a more common example of what mirages look like. If you're out in the desert and you're dying of thirst, that looks like water, and you run toward it and you get there and it's just sand. So that wasn't water, that was air up above. This is what a mirage looks like in Antarctica, in the South Pole. It's the same phenomenon. It's just that the air layers are reversed. Instead of having warm air at the surface and cold air above, because of all the ice, the air is actually colder at the surface and warmer above. And so rather than flipping the image down, it flips the image up. And so what you're looking at are these mountain ranges where the mountains have been flipped up in the air, like they're balancing on the peaks of the other mountain range. This is the Mirage. As I mentioned, clouds are little tiny droplets of water. And so as the air masses move, those droplets of water can take different shapes, such as these rippling effects, just like you would see on a beach. But instead of on a beach moving sand grains, it's clouds moving water droplets. But it's the same basic phenomenon. It indicates that there's a boundary. In this case, between air masses. On the beach, it would be a boundary between the water moving over the sand. But as it moves, it creates this rippling effect. The point is this going to give you an idea of how the air is moving? It's moving along these ripples. It's not moving in this direction, but this direction. All right, we've talked about the atmosphere. Now we're going to plunge down into the hydrosphere, the ocean systems. Do you have any questions about the atmosphere before we leave? Okay. In the ocean sections, we looked at the magnetosphere, the atmosphere, and now the hydrosphere. Just as the atmosphere is very, very thin compared to what we think, it's just a thin vapor of air hugging the earth. It's the same way with the oceans, the hydrosphere. We think of it being lots and lots of water, and it is a lot of water compared to us, but it's not a lot of water compared to the earth. What they've done in this diagram is they've taken all the water of the earth and they've shown it in one drop. So that's the water on earth. And this tiny drop next to it, right here, that's fresh water. So that's all the water, and this is fresh water we have to drink. So in other words, our water resources are very, very small compared to the earth as a whole. And when scientists talk about we need a planet with lots and lots of water, even our planet doesn't have that much water compared to the size of the planet. Part of the reason that's the case is that our oceans are really quite shallow compared to the earth. The average depth over our oceans is about 1.5 to 2 miles deep. So you're driving on the highway, think about how far a mile is, then turn that downward, that's how deep the ocean is. So they're actually much more shallow than the atmosphere even. Probably the most important aspect of our hydrosphere is what's called the hydrologic cycle. At least that's what it was called when I was in school, hydrologic cycle. Hydro was a reference to water, and so now they've just translated the Latin, and so they call it the water cycle. It's a process where water is evaporated off of the ocean. This process of evaporation causes condensation once the air cools and forms clouds, and those clouds can be blown inland. As the clouds are blown inland, they lose their water through precipitation. That's the fall of hail and rain back to the earth. Sometimes it's stored in ice caps and glaciers above the snow line, and it melts, and all of that precipitation, water flows back due to gravity to the ocean in a process called runoff. It can flow on the surface as stream flow, but it also can go underground, discharge. However, only about 1% of discharge is underground. Most of it's at the surface as rivulets become streams and streams become rivers, and rivers eventually flow back into the ocean. The evaporation is pure water that's evaporated. It's the reason when the water's bad, they tell you to boil the water, because if you capture the water after it's boiled, anything that could hurt you remains in the pot, and you capture the water and you can drink the boiled water. Well, that's what happens on the ocean. The evaporation removes pure water, And as it runs back to the ocean, it's carrying all kinds of salts and other minerals that it's dissolved from the rocks and the soil. And when it gets back to the ocean, it leaves those behind in the next process of evaporation. And so what that means is the oceans are salty because they're getting more and more salty throughout the lifetime of the earth, because the evaporation is pure water and the runoff water has lots of salts that are being carried to the ocean and builds up there over time. All right, this is the hydrologic cycle. It's God's way of irrigating, of watering the earth. Any questions on that? The key components are condensation and precipitation in terms of processes. We saw that when we looked at the equatorial regions, the water is being evaporated from the Sahara Desert and Kalahari deserts being carried back to the equatorial region.
Moisture rising as water vapor from the surface of the sea is blown inland by wind. On reaching mountains, the moist air is forced upwards, and as it cools, it condenses into cloud and finally rain. The source of precipitation, all fresh water.
And gravity carries it back to the sea.
There is a tropical downpour here almost every day of the year. Freshwater's journey starts here, high in the mountains. Growing from humble streams to mighty rivers, it will travel hundreds of miles to the sea. Angel Falls, the highest waterfall in the world. Its waters drop unbroken for almost 1,000 meters. Such is the height of these falls that long before the water reaches the base in the Devil's Canyon, it's blown away as a fine mist.
But it does congregate at the bottom and forms a rivulet that flows out. So it just transferred in a cloud for a short period of time. All right, we're talking about the hydrosphere and talking about some of the basic characteristics. Another is the fact that water has a high specific heat. That means that it absorbs heat slowly and it releases heat slowly. There's something called the hydrogen bond within water that gives it a springiness, to where once the heat is absorbed into the water, it stays there. It releases it very slowly. And that's a good thing because it creates what they call the thermostatic effect. The oceans of the earth act like a thermostat to help equalize the temperature, especially for populations living along large bodies of water, such as the oceans. You can see it here in this photograph. You see how the trees are greener right along the lake shore? And then as you move beyond the green trees, you can see the trees in the distance are changing colors. The reason is the trees along the shoreline didn't get the memo that it was wintertime, because the water is warming them, and they still think it's summer. So they haven't changed their colors yet. They haven't put on their autumn garb, as they say. Here's another example where the trees are greener right along the shoreline. During the summertime, the body of water absorbs heat from the air. That cools the air. But then as fall arrives and the trees begin changing colors in the distance because the air is getting cooler, the water is releasing that warmth that it's absorbed during the summertime, and throughout the fall into the early winter, it's releasing warm air for anybody living along the coastline. So it moderates the temperature. And so during the wintertime, as it's releasing the heat and warming the air, the water itself is becoming colder and colder. And so then as spring arrives and the air temperature begins to warm up into the summer, now you have the cold water of the lake. And because it's so cold, it's actually absorbing heat from the air. And so if the water is absorbing heat from the air, it's cooling it. So it cools during the summertime and it warms during the wintertime because of that bounciness, that springiness, and capturing and releasing heat very slowly. You may have experienced the high specific heat of water if you've ever taken a bath and you turn on the water and it's way too cold. You put your toe in there and say, wow, I can't get in, this is way too cold. So you turn it all the way to hot. And so you have a bunch of cold water and you put a bunch of hot water in there and you think, well, it will be nice and temperate. But then when you get in, you realize that the one part's really hot and the other part's really cold. So you have to kind of stir it up to get the mix, because the flow of heat in water is quite slow and it creates that differential. So whenever you look at the Earth's population, you see that most of the Earth's population is along the bodies of water. It's not in the interior. Remember, when you get into the interiors, they generally have lower population. And this is even with heating and cooling that we have today. You can imagine the past probably even more pronounced. Another feature of our hydrosphere is something called tides. The ocean surface doesn't remain the same. Twice a day, the surface rises and falls. They call that a tide. What's creating the tides, the bulges on the ocean surface? It's the moon. The moon, as I mentioned, is quite large compared to the size of the Earth, and its mass gives a tremendous gravitational pull. It pulls the Earth's surface up to a certain extent, but it certainly pulls up the surface of the water, because water is a fluid and it can change its shape. So that red dot that you see there, that's the high tide that's right below the moon. And so as the Earth rotates from east to west, the continents rotate into that bulge. And so Spain is rotating into the red bulge, so the tide on the coast of Spain is going up. Once Spain is on the other side of that red bulge, then the tide goes down. So it's rotating in the bulge and out of the bulge. Okay. The sun also, the gravitational pull of the sun also pulls up the tide, depending on where the sun is. If the sun is on the same side as the moon, which would be a new moon, you're looking at the dark side of the moon. So if you have a new moon, the sun and the moon are on the same side, they're pulling together, you get really high tides. So you can get high tides during a new moon because they're pulling together. During a full moon, when the sun's on one side and the Earth's on the other side, they're pulling against each other, so you get lower tides. You still get tides, they're just not as high. All right. This is a GIF that I found on the internet that shows that bulge. Of course, they've exaggerated the bulge. but it's just showing as the moon orbits the Earth, you can see the rotation there of the tidal bulge. Also, you can see when it's on the side of the sun, right there. See how big it is? Because they're pulling together. On the other side, they balance each other out. The height of the tide is also determined by the geography, the shape of the ocean floor. And so there are certain places where the shape of the ocean floor can actually funnel the tidal effect. One of the more interesting is in the Bay of Fundy in Newfoundland. Those aren't flying fish that they caught in their nets. During high tide, those nets were about 4 feet below the surface of the ocean. And those fish got caught in the net. Then the tide went out and they're suspended up in the air. So the fishermen have to climb up to get the fish out of the net. The Bay of Fundy has about a 4 or 5 meter tidal fluctuation twice a day. That's about 12 to 15 feet. So it affects the boats in the harbor too. Twice a day, the boats are sitting on the beach. Then the tide comes in and they're up in the port. Then they're on the beach and they're in the port and so on. So probably quite a bit of damage to those boats because of the high tidal range. Another feature of the oceans is that they circulate. Because of the Earth's rotation, it causes the water in the oceans to form a giant helical gyre. And the motion in the oceans is clockwise. So in the North Atlantic, the water is circulating like this. And because it's moving northward along the Western Atlantic and southward along the Eastern Atlantic, it can actually create a concentration of debris, especially seaweed, near the center. Just like if you pull the plug in the sink and you got a bunch of soap bubbles, as it spins down the drain, the soap bubbles will congregate in the middle. Same thing with the seaweed. You can see it here if you look carefully. That pattern, that's the seaweed in the middle of the Atlantic. At least the pattern's created by it. They call that the Sargasso Sea, the center of the North Atlantic, the Sargasso Sea, because the type of seaweed that primarily forms that is Sargasso. This is what the seaweed looks like if we sail into the Sargasso Sea. And up close. There's not only a circulation in the surface currents, there's also deep currents that circulate. And it's very similar to basically the same physical issues that we saw in the atmosphere. When things heat up, they expand, they're less dense, they rise. When things cool, they contract, they become more dense and they sink. Well, the ocean's the same way as the waters move in the gyre northward, they're moving in the colder regions. The water cools and contracts and it sinks. In the northern sea, it hits the bottom of the ocean and it spreads southward in these deep ocean currents. It's almost identical to what we call a cold front. Cold front, the air at the polar regions cools and contracts and it moves southward along the surface, creating these cold air gusts. The same thing happens in the North Atlantic. The water cools and contracts, it sinks to the bottom, then it spreads southward like a deep sea cold front toward the equatorial region, where the surface warm up. As they warm up, they expand and move northward. So what that means is that you have warm surface water moving northward and you have cold deep water moving southward. Okay, and then the water in between doesn't circulate at all. So there's a distribution of water not only horizontally around the shores of the Atlantic, but vertically from the surface to the deep water. This is a diagram just showing the warm water here in the Gulf Stream moving north and becoming cooler and cooler. When it gets to the North Atlantic, it becomes cold and it drops down and moves southward below the bottom of the ocean. What's fascinating is there's a particular area right here by Greenland where that shift takes place. And there's one part where you can even see it. Now, this isn't the whole thing, but you see how the water is descending down to the deeper part of the ocean in this area, in that particular valley. Right here. It's like a waterfall that's like 11,000 feet. And just a short distance, it plunges down to the bottom of the ocean, which is kind of This is a video clip. This is a video clip where they have a tethered camera to a balloon, and they elevate it so you can actually see where that cold water descends back to the bottom. The North Pole is actually a sea called the Arctic Sea. It's covered with a thick cap of ice. And during the Cold War, Russia and the US had all kinds of military intrigues with our nuclear submarines doing all kinds of reconnaissance of that area. The fear was that Russia would send a nuclear submarine under the ice caps, break through near Canada and shoot a nuclear missile over Canada into the US and so on. This is a photograph that was taken of one of those nuclear subs breaking up through the ice on the Arctic Sea. The North Pole is not on land. It's actually on the sea, but there's ice covering it. I don't know if you can see the GPS there. You see the position 89.56. So that's 4/10 of a degree from the North Pole. So if you ever wondered what's the North Pole looks like, there you go. There's no pole, no candy stripe pole, no Santa Claus workshop or anything. But yeah, this is about as close as I've seen to the North Pole. Basically just ice. So if we photograph the Earth from above, you can see North America here, the Eurasian continent there, and then there's this ocean covered in ice. If we melted the ice, it would look like this. Just a sea. Here's a cutaway showing what it would look like. And photographs along the edges that shows the ice sheet. It's much thicker in the interior, but this is along the edges. You can see the sunlight filtering through the ice. The South Pole is different. The South Pole actually does sit over a continent. The continent is, what's the name of the continent, South Pole? Antarctica, that's right. And you can see the peaks of the continent sticking up through the ice along the edges. The interior ice is estimated to be about 7,000 feet thick. So that's a mile of ice in the middle. So essentially what we'll explore later is a continental glacier. Around the continent of Antarctica, there's something called sea ice. Much like we saw at the North Pole, that sea ice will grow out during the wintertime, and then during the summertime, it melts back to the continental edge or shelf. You guys do know that in the South Pole, in the Southern Hemisphere, the seasons are reversed. So if you're going to South America during Christmas time, you would want to take your bathing suit because it's their summer. Our winter is their summer, and our summer is their winter. Here's a photograph taken by a tour group of the outer edges. This is during the summer, which is our winter. You can see the sea ice is melted all the way back to the edge of the continent there. During their winter, the sea ice extends far out from the edge of the continent. Anyway, this is one of the ridges that's exposed there in Antarctica. If you take away all the sea ice, this is the shape of the continent. And a great photograph of the sea ice at its maximum. During the summertime, the sea ice breaks up and melts and flows back into the sea. And as it does, it creates large icebergs. Icebergs will melt into these beautiful sculptural forms. It's the land of the penguins and the whales, very common sites for tourists. Matter of fact, if you go there on tour, they'll show you the flocks of penguins and the herds of whales and so on. Geologists have worked along the edges of the rock ledges of Antarctica, and lo and behold, they found fossils of ferns, which would imply that at one time in the past, Antarctica was actually quite warm, that ferns could grow there. However, if Antarctica was so warm that you could grow ferns at the South Pole, the equatorial regions would be too hot to support life. And so it was a great mystery up until the 1960s and 70s, as geologists began coming up with a new idea about the lithosphere of the Earth. It's called plate tectonics. You may have studied it in 8th grade. Now it's more common in science today. And plate tectonics teaches that the continents actually move. They migrate around the Earth's surface. And so whenever this fern was alive, Antarctica wasn't at the South Pole. It was near the equatorial region. And it has since shifted due to continental drift to the South Pole. And that's a good introduction to our next stage, which will be looking at the lithosphere. So we've looked at the magnetosphere, the atmosphere, the hydrosphere, and the lithosphere.